Okay, so let's continue today's lecture. So we are on chapter 2. We will try to finish this chapter today about existence of invariant measures. Invariant measures. So as I said, this is a little abstract, so it's an existent result. So remember, this is a theorem we wanted to prove, which is that if we have M is a separable metric space, F from M to M continuous. So this implies that then there exists an invariant measure. There exists an invariant measure. Okay. So remember, the way we said we were going to do it, an invariant actually is a probability measure, an invariant probability measure. I said that the way we were going to prove it, we have two ways. So there is a direct proof just using the push forward, like the F star, which is a push forward operator, like having a fixed point, or also you can average. You can average. In both proofs, we needed to put a topology on the space of measures. So M is a space of Borel measures, and M1 subspace of M is space of probability measures. Okay, and remember we had F star, the push forward operator, which acts from M to M. And one way we wanted to prove this theorem was to use, as I said last time, a fixed point theorem that requires this map to be continuous, that requires putting a topology here. So remember, tau star is a weak star topology. And last time we had proved this theorem that tau star is metrizable. Okay. So tau star is metrizable. Then whenever we want to prove compactness, we just prove sequential compactness, and also continuity, we just prove sequential continuity. All right. So let's recall. So for today's lecture, let me recall this theorem. So this is a theorem from topology that we will use. Theorem Schauder Tikhonov. So this is like for general vector space, let V be a topological vector space. Okay. K subset of V compact and convex. K is compact and convex. Okay. If you have F, which is from V to V continuous, with it lives invariant this compact set is a subset of K. So the theorem tells you that then there exists V star in K such that F V star equals V star. So there is a fixed point. V star is a fixed point. So, yeah, so we are going to apply this theorem. This is a result from topology, so we will not use it. So we will apply this theorem for V being M, the space of measures, and K is M1, the space of border probability measures, and then F, our application, is F star. So there are a few things we need to check. We need to check that M is a topological vector space. M1 is compact with the topology we have, and F star is also continuous. So we have these 4 bits topological vector space, compact and convex, continuous. So the easier is that M is a topological vector space. So a claim is that M is a topological vector space. So we all know what a vector space is. It's just like it is linear, you know. You can do multiplication by constant. You can also do addition. So M is clearly a vector space because of linearity of the integral. So this is what I'm saying. If you have the integral of phi d mu1 plus d mu2, this is just the integral of phi d mu1 plus the integral of phi d mu2. But to check that it is like a topological vector space, you need to check that the addition is continuous as an operator. So topological, it just means that this, which is defined from M times M to M, is continuous. Okay. Whenever now we say continuous, we know we're talking about the weak star topology. Okay. We have spent almost last lecture talking about this topology. So which is when you take 2 measures, mu1, mu2, it just gives mu1 plus mu2. Also, the multiplication by scalar also is. Okay. To check that this is continuous, you can just see that if you have mu n converging weak star, so this is the product topology you have here, converging to mu, and nu n converging to nu, so this is star. So do we have that mu n plus nu n is converging weak star, to mu plus nu. So everything I'm doing here, I can do it sequentially because I know I am in a metric space. Okay, the topology is metrizable, so I can just and this you just get it by just doing the characterization of this with respect to the integral. So we know that this. So this is a characterization. This is equivalent to saying that, this part here is equivalent to saying that the integral of phi d mu n is converging to phi d mu, and also the integral of phi d nu n is converging to the integral of phi d nu, right? So for every phi continuous bounded, and you just do, these are convergence real numbers, so you have that the integral of phi d mu n plus nu n is convergent. So this is just, everything here follows from linearity of the integral. Okay. So this is a topological vector space. So this guy is okay. Now let's prove that this topology M1 is compact. Theorem. M1 is weak star compact. So proof to prove this, it's just enough to prove sequential, as I said, sequential compactness. Like if you have a sequence, you can find a subsequence that converges. So enough to prove sequential compactness. Everything is because we have a metric. Right? Yeah, enough to prove sequential compactness. So what do? We take, let mu n be a sequence in sequence of probability measures. So what do we want? So we want this to find subsequence mu n j such that the integral of phi d mu n j is converging to the integral of phi d mu, where mu is a measure that is the limit. Okay, so if you just look at this quantity here, for a given function, this is a sequence of numbers that are bounded. So clearly, you could have a subsequence for which it converges. But here the problem is that you want a subsequence that works for all. That works for all continuous functions, because if you fix this guy, you find a subsequence. The subsequence you would find will depend on the function, on this function. So to do that, we use the condition about separability here. That M1. This is also a result from topology that we will just use. M being separable implies that C0M is also separable. So that means that you can take, let phi 1, phi n, and so on be a countable dense subset of C0, be a countable dense subset of C0M. So here there is something you can do, because so if we have a subsequence that works for all of these guys, then we can hope to get that this subsequence works for all others, because this is a dense subset. Okay, so the idea is to find a subsequence that works for all of these guys, and then do it for general function by just using the fact that this is dense. Okay. What do we have here? We have that for phi 1. For phi 1, if you fix phi 1, you can find a subsequence mu in 1. So let me look at the notation I have here too before I, yeah. So I can find a subsequence n 1 1 and 1 2 and 1 3. So this one is just because I'm taking this phi 1, okay? This one is related to this. N k 1 and so on. So you can find these subsequences that this is converging. Phi 1 d mu n 1 j is converging to something. Okay, it's converging. Okay. So this, as a sequence of real numbers, is converging. Okay. See, what I said here is that this is for fixed phi. This is a sequence of real numbers that is bounded, so you can find a subsequence that converge. So that's what I do here. So if you take phi 2 here, you can find another subsequence. But here the trick is to choose this subsequence so that it works for the previous function as well. Okay? The trick here is the subsequence you find here should work for this guy also. So you find n 1 2 n 2 2 n 3 2 n k 2 and so on, such that this guy converges for phi 2 and also it converges for phi 1. For it to converge for phi 1, I can just choose this subsequence to be a subsequence of the one above. Okay, you choose this guy as a subsequence of this one. Okay, so such that this guy, this sequence here of phi 2 d mu n j 2, and this guy is also phi 1 d mu n j 1 n j 2, sorry. They both converge. This you can do it by, to guarantee this, you need by choosing n to j as a subsequence of n1j. The subsequence you take here, consider as a subsequence of the one above. So for phi 3, you do the same. You take n31, n32, n33, and so on, nk3, and so on, so that you have the convergence for, you choose this subsequence as a subsequence of this one above. So you will have convergence for all three, okay? So that we have convergence, and so on. So the idea is to take the diagonal subsequence. You take this guy here, the diagonal subsequence. So you take n What is the notation for that? Yeah, you define Lj as njj is a subsequence says that the integral of phi n d mu Lj, this guy as j goes to infinity, is converging to something that depends on, so we just write it as this, as a function that depends on phi, okay? It's something that depends on this function for all so at least I have a convergence for all of these guys. I have a subsequent that works for all of these guys here. Now to do general function, so claim, so if you pick, so the claim is that this subsequence Lj works for all continuous function. So indeed, if you pick a continuous function, you can find, because this is dense, so for every epsilon positive, there exists n epsilon such that phi n epsilon minus phi c0 is less than epsilon. Okay. So in particular, you have phi d mu Lj minus phi n epsilon d mu Lj, because the two functions are nearby and these are probability measures, so you have that this is less than epsilon, strictly less than epsilon. But here there is one, I will not call it a complication, but we don't know yet whether this guy converges. Yeah. But from here we can know, we can have a bound on the lim sup minus the lim inf. So from this, you can have that the lim sup always exists, okay, of phi d mu j mu Lj minus the lim inf of d mu phi d mu Lj is less or equal to epsilon. From this, from the fact that they are both, this sequence is close to a sequence that is converging by epsilon. So the lim sup minus the lim inf will be less than 2 epsilon. And since epsilon is arbitrary, you can see that the lim sup is the lim inf is the limit. So since epsilon is arbitrary, then this guy exists. The lim sup is the lim inf is the limit. So the integral of phi d mu Lj is converging to a function that depends on phi. I haven't said nothing about this function, okay, yet. So it's just something that depends on phi. I call it f phi. Now, Now there is, so we have the convergence, a subsequence that works for all, but we need to find this measure mu star. This guy here. We need to find this guy here. Okay? So this measure should have something to do with this function. Okay? Our goal is to say that this is the integral of a measure. So let's see what is this functional. So see that f is linear. Okay? So this is what I mean. If you take f of lambda phi equals lambda f of phi, and f of phi 1 plus phi 2 equals f of phi 1 plus f of phi 2. This just from the linearity of the integral. This guy, write it as, this guy is the limit when n goes to infinity, when j goes to infinity of lambda phi d mu n lj. Okay, so this lambda goes out. You see that this will be lambda times the limit when j goes to infinity of phi d mu n lj. Okay, and also this one similarly. So everything follows by linearity of the integral, and we have the same subsequence that works for all. And also see that f of phi is positive for phi positive. So if the function is non-negative, then this functional, now I can call it functional, it's linear. This functional is also positive. Okay, this is also easy just from the definition. Now there is this theorem from measure theory that we will use, which is if you want to find, so there is this Riz-Markov representation theorem. Markov representation theorem, which is, you know, related to something what Jean was asking last time about, you know, the weak star topology, how it's related to the weak star topology that we see in functional analysis. So these measures are really functional. Okay, a linear operator on continuous function that satisfy this property. So what does it say? This theorem tells you that f from C0m to R that satisfy f of phi positive for phi positive, non-negative, okay, and f linear, then there exists a Borel probability measure, mu such that f of phi is the integral of phi d mu for all. Yeah, this is general from measure theory, and moreover, mu is in M1 if and only if f of 1 is 1, the constant function 1. Okay. So this you can find if you haven't seen it before, you can check in this book of Rudin. It's theorem 6.19, and the title of the book is Real and Complex Analysis. So real and complex analysis. So it is just about duality of these measures, so complex analysis. So you can find the book there. So it is more general. Actually, you could have here a complex function. So we are just going to use it. It's okay. So from this theorem, so using Riesz-Markov, there exists mu in M1 says that we have mu n Lj's to mu. So this finishes the proof of compactness. And yeah, and then we have everything to apply Shauder-Tikhonov, okay? So we have V, so apply Shauder-Tikhonov I think it's like this. For the vector space is M, our compact set K is M1. Oh, did I prove continuity? No. No, we haven't proved continuity of F star, did we? No, we haven't. We haven't. So we are left to prove, so to apply Shauder-Tikhonov, we are left to prove that F star is continuous. Right, so lemma F star is continuous. So let's do this real quick. So to prove continuity, here we can do it actually using the definition of the topology, using the basis of neighborhood. You can pick, where is this? Yeah. So you pick mu on M, and you consider phi like a set of continuous bounded function, bounded, and then epsilon positive. You have that this guy is a neighborhood of V. Remember, V mu C epsilon is a neighborhood of mu. So you wanna see that, you wanna find so the idea is to find another neighborhood. So find another guy V of mu phi prime epsilon prime, such that this guy f star minus 1 of v mu phi epsilon is a subset of v mu phi prime epsilon prime. What did I do? Oh, it's e. Oh, so this is what I want to say. So this guy should be f star mu. Yeah. Yeah. Is it? Yes. So the idea is just to no, this is what I want to say. So, sorry, f star, this guy, maybe f star mu phi prime epsilon prime. Yes, sorry, this is what we want to find. Yes. So we are the image. Yeah. So this is saying that f minus 1 of this guy is a subset of that. Yeah. So it takes me some time to see what I want to say. Okay. So let's see what is so see that for every function actually there's the integral of phi d f star mu equals the integral of phi composed with f d mu. So this for every function, for every phi. Sorry. This is actually not difficult to prove. You can just check it for the indicator function, for a simple function, and then do limit. So check for indicator function, check for indicator function, and so on. Okay. Indicator simple and use this dominated convergence theorem. Okay. So yeah. So basically what you do here, you define phi prime to be phi composed with f, which is phi 1 composed with f, phi 2 composed with f. These are continuous because f is continuous. This guy is continuous. It's bounded because phi are bounded. So this is continuous and bounded. And bounded. And from this will imply this part here. And epsilon prime is the same as epsilon. Okay. Yeah. So this is continuity. Yeah, this is continuity. Yeah. So from Shao-Drishikonov now we have our invariant measure. So this finishes the proof of existence. So remember what we have used here. We used the separability of the space and yeah. Compact, yeah, yes. I just realized now. Yeah, I just realized now that here we need M to be compact. That will imply that C0M is separable.
Yeah.
Where is that?
It was here.
Yeah, sorry, yeah. That's a good point. You can correct that. So, yeah, we needed M to be compact. Yeah, this M compact imply C0M compact and metric is separable. Yeah. Okay. So yeah, this is abstract. So let's see another direct proof of without shadow, the averaging direct proof of existence. So direct proof goes like this. You pick let nu be a probability measure. You define mu n as 1 over n, j equals 0, n minus 1 of f j star nu. Okay, so this will be also a probability measure. So M1 being compact implies that you have a convergent subsequence. So there exists mu nj a subsequence such that mu nj is converging to mu that is in M1, the weak star topology. Okay, and M1. So the claim is that this is a fixed point. This is a fixed point of f star. So let me give myself some more space here. The claim is that f star of mu equals mu. So we know that mu n, I will drop the subsequence, okay? I will drop the subsequence. Mu n is converging to mu. F star is continuous, sequentially continuous, so this implies that f star of mu n is also converging to f star of mu. Okay, but because of what we just seen there, sequential continuity, and here we can see another way to, to know the limit of this guy. So by definition, f star mu n, f star is linear. Did I check that? Yeah, I did not check it here, but we know that it's linear. When I say we apply shadow, so this guy is continuous, it's linear, okay? Sorry. Yeah, this is 1 over n, the sum j equals 0, n minus 1, f j plus 1 star nu. And this you can just rearrange here to have j equals 0 to n minus 1. See here, okay, so if I was writing it, not skipping any step, this is what I should do. So it goes from 1 to n of f star j nu. To see that mu n is appearing here, you need to add and subtract the take out the last term here and also add a 0 term. So which means you write this as 1 over n, j equals 0, n minus 1, fj star nu plus, so the last term is 1 over n, fn star nu, and the 0 term we added, we need to subtract it. It is minus f. Minus nu, sorry. Yeah. So it is easy to see that this converges to 0 weak star, okay? So check that this guy 1 over n fn star nu minus nu is converging to 0 weak star. Yeah, just evaluate it on functions. Use that nu is a probability measure, so you compound it, and that's simple. So this implies, therefore, what do we have here is that now f star mu n is converging weak star to mu, because this we know, to mu, yes. We know this is converging to mu. Okay? And this two limit has to coincide, which implies that f star. So this is another proof, a direct proof, and it is actually a proof that is very much used in dynamics. Like whenever you want to find something invariant, you just average along the orbit of any guy you start with, because nu was arbitrary, okay? And in dynamics, usually, depending on the measure you start with here, you can get a good measure, like a meaningful measure sometimes that you are looking for. For instance, if you have heard or read about SRB measures, like these physical measures, they call it, or scenario Bound measures, these measures for which you have, that must, you have good application of Birkhoff ergodic theorem, it depends on a specific choice of this starting nu, okay? So this is something that is very much used in dynamics, this proof. Yeah, so this is the existence. I will close this chapter here. And we go, before that, I wanted to give some more exercises. Yeah, there is this exercise actually that completes this chapter. The previous chapter also. So this is the North Pole, South Pole map. So you can consider that you are on S1. So this is the circle I'm considering, okay? Z minus I equals 1. So this is a circle centered at I. And this is the map. What is this map doing? So you have here, you have 0, 0 is here. This is the circle that I'm considering, so this is I. Okay. This is 2I. Okay. So what is this map doing? You take a point Z here. To know the image of Z, what you do is you draw the line from 2I to Z, which is just the projection. So this is pi of Z. The projection from 2I, you do this. You take half of this guy. This is now on the x-axis, so pi Z over 2, and you project it back. And this is t of Z. The point you get here is t of Z. So if you want me to write it clearly, this is what is doing. So T of Z is 2i if Z equals 2i. It leaves this guy invariant, and it is pi minus 1. So by projection, you understand what I mean here, projection. Is respect to this point. If Z is different from 2i. So the exercise is to show that every invariant measure of T is of the form P delta 2i plus 1 minus P delta 0. Okay, or 0, 0, 0, yes. 0 of C, of the complex number, to be. By the way, I just noticed that I forgot to check that the space of probability measures is convex. Because when you want to use Schauder, you need to check it's convex, okay? But that is simple, right? You just take any convex combination, so it will have, again, probability 1, like the measure of the whole space will be 1 again, okay? Yeah, I just write this is a convex combination of these two delta measures. Okay. So this is the North Pole, South Pole map. And also I want you to check these exercises from the book, which are 2.2.5, 2.2.6. This is the 2.2.7. For Antoine who are joining, we are using the book of Marcelo Viana and Cledo Oliveira about foundation of ergodic. Foundation of ergodicity, yes. So these exercises refer to that book. Okay. So I will stop here for this chapter, and I will start chapter 3 about ergodic theorems. Yeah, this is a very interesting chapter, as it is the title of the course. It is central. Maybe I will just give like a motivation of what we will see in this chapter, in this time we have. Chapter 3. Okay. This is ergodic theorems. So in this chapter we will see many, ergodic theorems. They have von Neumann, there is Birkhoff, there are many ergodic theorems. So here our standing assumption will be we have our dynamical system, which is measurable. Whatever I do here, I do it for, like when I talk about ergodicity, I mean invariant measures, F invariant. Though the definition of ergodicity that we will see doesn't use any, doesn't need F to be invariant. There are some people who study ergodic measures that are not invariant, but for this course we stick to invariant measures. So remember what we have seen from the first chapter is that if you have a Borel set, mi of E positive, we have Poincaré that tells you that this number j of fjx in E is infinite for mu almost every x in E. So this is telling you that the points, if you have a set of positive measure, this measure being invariant, that means that the point they tend to return to this set infinitely many often. In this chapter, we are interested in a refinement of this. Okay, we want to say more, not only infinite, but we want to see like the frequency of visits. The frequency of visit, like if I look at n, the orbit n time, like n orbit of length n, how many times the frequency that this point comes back to the set. So in this chapter, we are interested in the so-called the mean sojourn time, like the frequency of visits. Time, which is tau x e, which is the limit when n goes to infinity of 1 over n, the cardinality of less than n minus 1. Yeah, so we are interested in something that is finer than just saying that the number of visits is infinite, but now we want to know about the frequency. Or generally, you can say you take any observable, like any potential you choose, or generally you pick phi continuous or just measurable or integrable, mu integrable bounded. Yeah, we would, yeah, just we are just introducing. I will not put any conditions, but it's a function that should be at least integrable, mu integrable. So we want to know something about which is the limit when n goes to infinity of 1 over n composed with fi x I equals 0 n minus 1. Or j, let me be consistent with the notation here. So here phi is called sometimes observable or potential. Phi is a function that describes like what you care about for your system. Like phi can be a function in application that you know. For instance, if you are interested in a system that is predicting the time or the weather, phi can be a function that says that the temperature, the wind speed, or the rain forecast is in this region. Okay, so phi can represent this, and you want to know how many times you fall in that region. Okay, so yeah, so this is just the abstract, and see that tau of xe is just tau of x, this guy here, of the indicator function of e. Okay. And we also have the corresponding problem for flows, for continuous time system. So the corresponding problem for flows, like you have tau x phi is 1 over t the integral from 0 to infinity of phi composed with ft of x dt. Okay.
This results only for conservative systems, right?
Yeah, so that's interesting. So this is what we say invariant. So when you say invariant, you say conservative with respect to Lebesgue. So some people, they are just interested in, you know, this measure being Lebesgue, being the, you know, the physical, the measure you get from the structure, which is just conservative systems, okay, in general, okay. Yeah. So yeah, invariance, conservative is invariant with respect to Lebesgue. So we will see that if mu, we will see that mu ergodic, already invariance will imply something about this limit, that tau x phi, oh sorry, this is limit, okay. Yeah. So for ergodic, if you have an ergodic measure, you will have that this, yeah, sorry, I'm using different, compose ft x dt. This guy is converging to, so this is what I wrote in the introduction of this lecture, that say that time average is converging to space average here, okay. Or in this system, or in the discrete case, 1 over n minus 1 phi composed with fj x is converging to the integral of phi d mu. Yeah, and this is for mu almost every x. It doesn't hold in general for all points, but it holds for mu almost every x. So if you are like in a case that you just care about conservative system, you can see that this converges for almost every point in your space with respect to the Lebesgue measure. And yeah, we'll basically see these type of theorems, and yeah, something that is related to what we were discussing with Brandon and other people before the lecture, which is interesting, which maybe we will have time, maybe in the summer we can study this type of things. So, so just a remark. So this is not part of our lecture, but just an observation. So see that mu, we will see that mu invariant ergodic imply that you have 1 over n j equals 0 n minus 1 phi composed with fj is converging to phi d mu. So, but if your function was having mean zero, like if then what you would have is, then this would mean that 1 over n is converging to 0, okay? Now there are some interesting problems. Maybe we can study this in the summer, or I don't know, other things. Like when you change this weight here, can you put a different weight for which you have here a number? So question, is there a function like k that depends on n such that 1 over kn, this is going more toward large deviation, and more statistical properties of your system, but we will not do it converge to something, not 0. It happens that in most chaotic systems like 2x mod 1, like these expanding maps, you can see that if you put here square root of n, this is converging to a probability law that is a Gaussian. So in many chaotic systems, this is just a parenthesis that allow me to continue what we were discussing in most chaotic systems. So there is a way to put, to a Gaussian, like a probability law. Yeah, probably this we will not see this type of results for this course, but probably in the summer maybe we can study this type of thing that goes beyond, this goes beyond ergodicity. Now once you have this, can you do more? Can you do something? That is when we say that this is a deterministic system that is going to be random, because like you can just start with your map being 2x mod 1. This is deterministic. You know exactly the system. It is this guy. But at the limit, it's going to converge to something random. Deterministic tends to random. But yeah, anyway, this is beyond ergodicity, beyond mixing. But for this course, we will just stick to ergodicity and mixing. So maybe in the summer we can, see more on these type of results. Okay. Yeah, at least I can define something and then we stop. I will just write a definition, then we stop. Our first subsection is the von Neumann ergodic theorem. Okay, this is a type of ergodic theorem that is always dealing with, all ergodic theorem, they are dealing with time average and space average, okay? So before that, I will recall few facts from Hilbert spaces. So Hilbert space. So remember Hilbert space, we have the space which is H, we have a norm. This is a vector space. AKP is a norm. This norm comes from an inner product here. So this is our vector space. This is a norm, and this is an inner product. And we have the property that I will not write. So given a subspace F on H, you can define the orthogonal, its orthogonal is F set of V, as you might guess, such that V u equals 0 for all u in F. So this is orthogonal, and see that the space can be written as a direct product F and F orthogonal. So these are just recall to state our theorem. And remember orthogonal projection. I'm just guessing that everybody here has seen Hilbert space, and the property we will use here are just the basic properties. So orthogonal, I will just recall them orthogonal projection. So given F subspace, you have PF is the orthogonal projection H to F. As you can guess, it's just projecting every vector to PF V, for which V is written as, using that splitting, PF V plus V. Plus V orthogonal, sorry. So if it's like you write a vector in terms of its component on F and its component on this transversal guy, and see that P square F is PF. Okay, let's just do an example and then we stop here. A real quick example, which is actually the example we will use, is L2 mu, the space of L2 function with respect to a measure phi such that phi squared d mu is finite. And F. So I'm assuming here mu is a probability measure, or just mu is a finite measure is okay, but let's just take mu is M1. Because if it is a finite measure, you can always normalize it to write it as a probability measure. Space of constant functions. Okay. So L2 is our H here. H is L2. This is a subspace of L2 mu, which is our H. And this is clearly a vector space, because if you add two constant functions, you get a constant function. And yeah, you can see what is a projection of the orthogonal projection of this. So you can, and here the inner product, what is the inner product? Phi C is the integral of phi. This is L2 d mu, okay? This is the inner product. And see that the orthogonal projection of any function is its integral with respect to d mu. Yeah, to see that you can just, okay, this is a constant function. We expect the projection to be a constant function. We know the projection is the function, but we're projecting to a space of constant functions, so it should be a constant function. And yeah, to see this, you can check that PF is, you can write as, if you write phi as this PF phi plus phi orthogonal, so you can say this minus is this, and this is in F orthogonal. So in particular, it is orthogonal to the constant function 1. So in particular, you can say that phi minus PF phi 1 This guy is 0. So let me write it here. Okay, and yeah, and from here you can see that then PF phi 1 equals phi 1. This guy is the integral of PF phi d mu and phi d mu, and PF phi is a constant. You are projecting to a constant function, so this is a constant, and mu is a probability measure, and this is exactly PF phi. So yeah, this is the projection. Yeah, and I need to define the Koopman operator, but we will do that probably next week. Okay, so next week we will continue on this chapter, the Vernon. We will spend a good amount of time on this chapter because it's crucial for the course. It's very important for us. So the theorem we will see here is a theorem that is actually, it is strong in the sense that in this von Neumann, it is strong in the sense that, you know, the ergodic theorem, I was saying that we have these guys for mu almost every, and here you don't see any measure appearing because we have a you know a structure. We have more structure on the space. Here we have Hilbert space with matrix and so on. So we expect to have something strong ergodic theorem here that we will see next week. So Tuesday is a national, Wednesday is a national holiday, so we will not have lecture. So we will meet next week, Monday, and you guys will meet with Mateus this Friday. And by Wednesday, I will send also more exercises about the previous chapter. Okay, we stop here for today.